A car starts from rest and accelerates. This graph shows how its momentum changes with time. First, watch how the momentum rises quickly at first, then more slowly, and finally becomes constant. Follow the red dot on the graph and the car on the road below. On the straight section, momentum increases steadily, so the yellow arrow grows, and the red force arrow stays constant because the gradient is constant. On the curved section, the gradient decreases, so the force arrow shrinks and momentum increases more slowly. On the flat section, force becomes zero and momentum stays at 39,000. Part A. Use the straight section from 0 to 1.5 seconds. Read delta P as 18,000 and delta T as 1.5 seconds. The resultant force is the gradient, F equals delta P over delta T, which gives 12,000 newtons. Part B, Part 1. Show that P squared over 2m equals kinetic energy. Start from P equals mv, substitute into Ek equals 1/2 mv squared, and simplify to obtain the result. Part B, Part 2. At 6 seconds, red momentum 39,000 from the graph. Use Ek equals 5.4 times 10 to the 5 joules. Rearrange to find mass about 1.4 tons, or 1400 kilograms. Question 2. A factory motor lifts 37 kilograms of boxes vertically through 13 meters, as shown in Fig 2.1. Electrical energy from the power supply is the input. The motor converts it into mechanical lifting. Useful output raises the load, increasing its gravitational potential energy. Some energy is wasted as heat and friction in the motor. The load reaches the storage area at the top. Part A, Part 1. The total weight is W equals mg. With 37 kilograms and g 9.8, W is about 363 newtons. Part A, Part 2. Useful work equals force times distance, or mgh. That is about 4.7 times 10 caret 3 joules. Part B, Part 1. Electrical energy input equals V times I times T. 230 volts, 5.6 amps, 11 seconds, gives about 1.4 times 10 caret 4 joules. Part B, Part 2. Efficiency is useful output over input, times 100. That is about 33%. Part C. The other energy is wasted as heat in the motor windings and bearings, and some work also lifts the cage itself, which is not counted as useful output. Question 3. A plastic cup holds 0.24 kilograms of water at 22 degrees Celsius, as in Fig 3.1. A block of ice at 0 degrees sits above the cup, and the thermometer reads 22 degrees. The ice is dropped in. It splashes into the water. Thermal energy is conducted from the warmer water to the colder ice. The water cools to 6 degrees as the ice melts, and the thermometer falls in step. Part A. Conduction is energy passed on by molecular collisions. Water molecules touching the ice have higher kinetic energy, they are warmer and move or vibrate faster. They collide with slower ice molecules and transfer kinetic energy. Energy flows molecule by molecule from hot water to cold ice. Part B, Part 1. As the water cools from 22 to 6 degrees, we use Q equals mc delta theta. Mass 0.24 kilograms, C 4200, delta theta 16 degrees, gives about 1.6 times 10 caret 4 joules released. Part B, Part 2. In ice, molecules sit in a fixed regular lattice and only vibrate about fixed positions. In liquid water at 6 degrees, molecules are still close together but not fixed, they can slide past one another. Part B, Part 3. A metal cup warms water faster because metal is a good thermal conductor, while plastic is a poor conductor and insulator. So energy from the warm room is conducted into the water much more quickly through metal. Question 4. Fig 4.1 shows a converging lens drawn to scale, with principal axis, focal points F, and a 1 cm grid. Part A: light slows down when it enters denser glass. Because it meets the surface at an angle, it bends towards the normal. A change of speed at an angle is refraction. Part B, Part 1. The principal focus is the point on the principal axis where rays parallel to the axis converge after passing through the lens. Part B, Part 2. The focal length is the distance from the center of the lens to the principal focus. Part C, Part 1. The object O is 1.8 cm tall, placed 2.2 cm from the lens inside the focal length. Part C, Part 2. From the tip of O, 2 construction rays locate the image. Ray 1, parallel to the axis, then through F after the lens. Ray 2, straight through the optical center, undeviated. Part C, Part 3. The refracted rays diverge, so trace them back to locate I. There is no real crossing of light, the image is virtual, upright and magnified. Question 5. Liquid X is in a pan on an induction hob, as in Fig 5.1. Part A. A cloth wipes the surface. The fastest, most energetic molecules escape into the air. Those left behind have lower average kinetic energy, so the temperature of liquid X falls. Part B, Part 1. High-frequency AC in the coil produces a magnetic field that keeps changing. The changing flux through the iron base induces an EMF by Faraday's law, driving eddy currents that heat the base. Part B, Part 2. Heating gives particles more kinetic energy. They move further apart, so the same mass occupies a larger volume and the density decreases. Part B, Part 3. Warm, less dense liquid at P rises. Cooler, denser liquid sinks to replace it, a convection current that spreads thermal energy through all of liquid X. Question 6. Fig 6.1 shows a 9-volt supply, resistor P, an ammeter in series, and a voltmeter across the 4-ohm resistor. Part A. For a metallic conductor at constant temperature, current is directly proportional to potential difference. Other physical conditions must stay constant. Part B, Part 1. P and the 4-ohm resistor are in series, so their resistances add. The total resistance is 12 ohms. Using I equals V over R, the ammeter reads 0.75 amps. Part B, Part 2. The power dissipated in P is I squared R. Using the same current, 0.75 amps, and Rp equals 8 ohms, the power is 4.5 watts. Part C, Part 1. P is made from the same clay, so its volume is fixed. When the length is halved, the cross-sectional area doubles. Since R equals ρ L over A, the new resistance is 1/4 of the original, 2 ohms. Part C, Part 2. Now P is 2 ohms, so the total series resistance is 6 ohms. The current becomes 1.5 amps. The voltmeter is across the 4-ohm resistor, so V equals IR, 1.5 times 4, which is 6 volts. Question 7. A charged plastic rod is brought near a metal sphere. The key idea is that electrons move, but positive nuclei stay fixed. Part A: rubbing transfers electrons, not protons. Electrons move from the cloth onto the rod. The rod gains electrons, so it becomes negatively charged, the cloth is left positive. Part B, Part 1. A conductor has free electrons that can move through it. In an insulator, electrons are bound in place, so charge cannot flow easily. Part B, Part 2. The negative rod repels the free electrons in the metal sphere. Electrons move to the far side. The near side is left positive, while the far side becomes negative. Part B, Part 3. The near positive charge is closer to the rod than the far negative charge. Since electrostatic force is stronger at smaller distance, the attraction is larger than the repulsion. The sphere is pulled towards the rod. Question 8. We compare radon isotopes, complete an alpha decay equation, and use alpha scattering to infer the nuclear model. Part A. Isotopes have the same proton number but different neutron numbers. Both radon nuclei have proton number 86, so they are the same element. Radon-224 has 2 more nucleons, so it has 2 more neutrons. Part B. In alpha decay, nucleon number and proton number are conserved. The top numbers give A equals 218. The bottom numbers give Z equals 84, which is polonium. Part C, Part 1. Alpha particles are fired at a thin gold foil. At K, the great majority arrive almost straight through. At J, only a very few arrive after large deflections. Part C, Part 2. Most alpha particles pass through, so the atom is mostly empty space. A few are strongly repelled, so the positive charge and most of the mass are concentrated in a tiny dense nucleus. Question 9. We use Newton's first law, then explain why a planet in a circular orbit needs a gravitational force towards the Sun. Part A. If there is no resultant force, velocity stays constant, same speed and the same straight line direction. So F net equals 0 gives constant speed along a straight line. Part B. Venus moves in a circle around the Sun. The velocity arrow is always tangential, but its direction keeps turning. That changing direction means acceleration, so there must be a resultant force pointing towards the Sun, gravity. Part B, Part 3. For one complete orbit, distance is 2 pi r and time is t. Substitute r equals 1.1 times 10 to the 11 meters and t equals 5,400 hours. The orbital speed is about 3.6 times 10 to the 4 meters per second. Part B, Part 4. Planet X is closer to the Sun than Venus, that is Mercury. On the inner orbit it moves faster. A smaller radius means a greater orbital speed.